An autonomous vehicle travels at highway speed toward a stalled white truck. The cameras operate flawlessly, lenses clear and wiring intact. Yet, because blinding sunlight washes out the camera's dynamic range, the vehicle accelerates directly into the stationary truck. Historically, automotive safety focused entirely on hardware and software integrity. If a brake line didn't burst and the control unit didn't short-circuit, the system was considered safe. This baseline is defined by the ISO 26262 standard, which governs functional safety. Level 3 and higher autonomous systems present a distinct threat model. A software-defined vehicle can execute its programmed code perfectly, possess entirely functional hardware, and still cause a fatal collision. There is a strict divergence in engineering priorities here. On the left, ISO 26262 mitigates hardware failure, a physical breakdown of the machine. On the right, the sensor is mechanically intact but suffers from specification insufficiency. It misclassifies the white truck as a cloud because the environment exceeded its operational limits. To address this specific gap, the automotive industry adopted ISO 21448, commonly known as SOTIF, Safety of the Intended Functionality. SOTIF operates on a clear premise. High-level autonomy hazards do not typically stem from broken parts. They emerge from algorithmic limitations, extreme environmental conditions, and the unpredictability of human behavior. We can track how environmental uncertainty becomes a physical accident by following data through the vehicle's standard control loop: sense, plan, act. The first block manages OEDR. Here, raw data from radar, camera, and LiDAR converge in a sensor fusion hub. Consider an anomaly known as phantom braking. A vehicle approaches a tunnel, and the camera registers a dark shadow on the asphalt. The algorithm processes the visual contrast and misclassifies the flat shadow as a solid vertical wall. No fuses blew, the lens is not cracked. The failure lies in the algorithmic confidence threshold, which prioritized the shadow's geometry over its lack of radar density. This misclassification generates corrupted environmental data. Once this data leaves the perceptive layer, the downstream logic treats the phantom wall as absolute physical truth. A vehicle's OEDR is bound by the constraints of its sensors. Its reality is entirely dependent on its ability to filter ambiguous physics. The false data packet now enters the system's strategic decision maker, the plan block. This block contains the driving policy. It acts as the vehicle's strategic intelligence, continuously weighing traffic laws against safety protocols and passenger comfort. To navigate these variables, the policy relies on intended behavior, a rigid set of rules defining exactly how the vehicle must maneuver given a specific data input. The rulebook dictates that an imminent collision with a solid wall requires maximum deceleration. The system rapidly issues a command for an emergency stop, responding accurately to the false positive. The driving policy logic executed without a single computational error. A perfectly logical driving policy remains structurally dangerous if it accepts inputs blindly, lacking the architecture to weigh the statistical uncertainty of its own perception. Preventing these logical traps requires moving beyond simple if-then rules. Real-world driving presents contradictions where following the rules ensures an accident. The classic example is the Type 1 dilemma zone. A vehicle approaches an intersection as the light turns yellow. There is insufficient distance to stop without a heavy rear-end collision from a tailgating truck, but maintaining speed guarantees running a red light.
This equation is a utility function. Under SOTF principles, the system relies on this mathematical calculation to resolve the ethical deadlock. The system continuously calculates the exact probability of a rear-end impact from the trailing truck versus the probability of a side impact collision if it enters the intersection early. These probabilities are multiplied by designated weighting variables. The engineering specification deliberately assigns human injury a massive mathematical penalty, while the cost of a traffic violation is reduced to a fractional weight. The equation resolves. The system calculates that a controlled intersection crossing carries a vastly lower risk to human safety than a guaranteed rear-end strike. It intentionally runs the red light. The architecture must possess the mathematical context to know when breaking the law is the safest possible action. That decision moves into the final block, act. This triggers the dynamic driving task, or DDT, which executes the physical steering, throttle, and braking. A vehicle operating with a thin performance margin can trigger a hazard entirely through misunderstanding context. The brake actuator functions exactly as instructed, but the sudden physical deceleration causes the accident. Yet inside this perfectly controlled loop sits the single most volatile component in the entire system architecture, the human passenger. Consider a driver utilizing basic adaptive cruise control who assumes the vehicle is operating under full Level 3 autonomy. They look away from the road to check their phone. Under SOTF, this mode confusion is not dismissed as user error. It is categorized as reasonably foreseeable misuse. The engineering burden expands. It must mitigate physical limits, compensate for logical blind spots, and actively predict human negligence. If a vehicle must account for infinite environmental anomalies and unpredictable human behaviors, mathematical certainty becomes difficult. How do engineers validate systems against scenarios they haven't thought of yet? This SOTIF evaluation matrix categorizes all possible driving conditions. Scenarios are plotted based on whether they are safe or unsafe and whether the system's engineers know they exist or not. The critical vulnerability lies in Area 3, the unsafe unknowns. These are the bizarre edge cases, like a kangaroo jumping into an Australian road, that the training data never encountered. The engineering objective is systematic discovery. Engineers force the system through millions of simulated miles to expose Area 3 anomalies. Once discovered, the anomaly becomes a known unsafe condition. The driving policy is then patched, shifting the scenario into the final quadrant, a known safe response. Validation in autonomous engineering is a continuous mathematical hunt to shrink the universe of unknown threats. This continuous cycle of discovery, analysis, and patching forms the foundation of the vehicle-level SOTIF strategy, or VLSS. It forces a hard separation between verification and validation. Verification checks if the engineers built the product exactly to the specifications. Validation proves that those specifications are actually sufficient to survive reality. Proving that safety profile physically would require billions of accident-free testing miles. Engineers rely instead on highly accelerated virtual testing to hit probabilistic targets. ISO 26262 answers the mechanical question. It ensures the sensors, actuators, and code operate without failure. ISO 21448 provides the technical framework for an intelligence that expects incomplete data, calculates its own uncertainty, and knows how to navigate a chaotic reality.